So here's a code to help you visualize one of the more challenging yet intriguing concepts in electricity and magnetism, Faraday's law. One of the ways you can set up Faraday's law is to have a magnetic field that is changing with time. That's what we've got here in the animation. We have a white arrow representing a magnetic field. The magnetic field really fills this entire region. We're just drawing one field vector to illustrate it, but just imagine this is permeating everywhere in space. And you have something about the magnetic field changing. The magnetic field is a vector, so maybe you have its magnitude changing. Maybe you have its direction changing. Maybe you have both changing. And what happens is when you have that changing magnetic field, you induce an electric field. So the electric field is represented by the yellow arrows here, and you can see that they're going around in a circle. And right away that's intriguing, because before you get to this point in Physics 2, all the electric fields that you work with come from electric charges, and that means they spread out of positive charges and go into negative charges. They never curl around. If you're only ever working with static stationary charges, then you can never get an electric field that curls around. You can get it to bend, right, like in a dipole, but you can't ever get it to go all the way around in a circle. A couple things you might notice already from the animation before we even get to the code is that the electric field is changing with time, just as the magnetic field is changing with time, right? So I have a magnetic field. It looks like it's oscillating, maybe according to some sinusoidal function, and so my electric field is oscillating as well. You also notice that the direction of the field changes. Right here it was going counterclockwise. Now it's going clockwise on the screen, and it keeps oscillating back and forth. So why don't we take a look at the code and see how we create this. The most important thing in this code is lines 5 through 9. This is where you control the magnetic field. So this is the magnetic field B as a function of time. B field is a vector, so we have to define the components Bx, By, and Bz. So in this case, we've gone pretty simple with it. We've set Bx to oscillate like the cosine of time, and we've set By and Bz equal to 0. So there's nothing going on in the magnetic field in the y and z directions. It's just pointing along the x-axis or the negative x-axis here. And so we're going to return that as a vector object here. Then in order to create these electric field vectors, we've set up some observation points. So this is literally just the points in space where we're interested in drawing the electric field. The electric field exists everywhere. We can't not have an electric field somewhere. These are just the points where we're asking the code to draw those electric field points. So for example, I might add more to this. I could copy and paste this line and add another set maybe a little bit farther down the x-axis. So these are both at, all these points are at x equals 0, right? See how they're centered around the origin there. I could move them a little bit farther up the x-axis. So now I'll have 2 rings of electric field vectors, right? I could make as many of those stacks of rings as I wanted to, right? I could go copy, paste, paste, paste. Maybe a 0.2 and a negative 0.1 and a negative 0.2. And what you'll notice is that we get this nice little cylinder of electric field vectors. So you have to imagine this kind of going everywhere in the universe, really. Another thing I could do, I could make the ring itself smaller. So maybe I take one of these rings of observation points and I make it, let's say 3/4 the radius of the other circles. And you see there I've got a little bit smaller ring there. So these electric field vectors exist everywhere. So when we see these things, just imagine them, you know, getting another version of each of these vectors at each point in space. Or you can add whatever kind of pattern you want. It doesn't even have to be in a circle. You could draw these in a square, whatever you want to do. Okay, next we create the visuals. I've got a note here that you shouldn't need to change anything beyond this point unless you really are looking to experiment with what's going on in the scenario here. Maybe you want to add a second changing magnetic field, or maybe you want to make magnetic field a function of position, right? So this magnetic field is uniform in that it's only depending on time. It's not constant, but it is uniform. So you could add in a function of position here. Maybe you want the magnetic field to change with where you're located. Let's see. Then we're going to draw the electric field vectors. So this is the list of arrows that we're going to draw at the observation point. So we're using the observation points to create these electric field vectors and work with those from then on. Whenever you create an arrow in VPython, you need a position. That's the starting point of the arrow. So you notice the arrow starting points are what's distributed along a circle here. You might notice that they always have a consistent starting point. And then axis is the direction and the length that they point along. So the axis is changing here. The direction is staying the same here, but it's stretching and shrinking, and then the direction changes to the opposites. You might notice that it's always pointing in the same direction there. That's interesting. Wonder if we can break that later. Then we set up the animation. We set up a time step to control our animation. That's how much time there is in between each frame of the animation. We set our time to equal 0 at the beginning because that's where we're starting. And then we have a scale factor to tell us how long to draw these electric fields, right? Because we're taking an electric field and representing it in position space. So this is just to control how long the length is. If your arrows are getting too big so that they're taking up the whole screen, you can make this smaller. If your arrows are too small to be able to see, you can increase this to make them longer. There's really no physics associated with that. It's just a display control. I set up a play pause button here, so if you want to, you can click pause to get an idea of what the thing is doing from one moment to the next. Oh, maybe you can freeze it at just the point where there is 0 electric field and try to figure out what's going on there. Then we got the animation loop here, so this is going to run for as long as true is true. So it's just going to keep running until we exit the program. We set an animation rate. You don't need to change anything about that. There's no physics there. Then as long as the pause button is running, then we're going to start calculating the magnetic field at each one of these locations, right? So we update the magnetic field here, then we need to update the electric field. And the way we update the electric field is by the derivative of the magnetic field. So the magnetic field is calculated in this B function, so in order to get its derivative, we're taking the magnetic field at just one step in time forward, and then the magnetic field at one step in time backward. So time is the current time. We're looking ahead one step dt, and we're looking back one step dt to get our 2 points to calculate a derivative, right? Yes, B is a vector. It still obeys the same derivative rules because you're doing derivative of the x component, derivative of the y component, derivative of the z component. It's really no different than when you're in physics 1 and you want to calculate velocity. You need delta x over delta t, delta y over delta t, and delta z over delta t. We divide it by 2 dt because the total difference between these is 2 dt, right? Because we go 1 dt this way and 1 dt that way. Total is 2 dt. Then we go to calculate the electric field. We calculate this using Faraday's law. So this here is where the physics actually comes in, because this is where we're taking a look at the magnetic field derivative. We are dividing that by the position here because it needs to decrease like the circumference of the circle that we're drawing, and we place it in the direction of E hat, which we figure out through a cross product. You might notice there's some perpendicularity going on here, so we have to have a cross product in there doing the right hand rule. And then we update time to keep moving forward. So what you can do with this, you can use this to explore this Faraday's law. So for example, what I notice is that my electric field lines disappear whenever this thing is at a maximum, right? It's just gone to its maximum length. Now it's going to start decreasing. Wait a minute, from Calc 1, I know that a maximum occurs where you have 0 in the derivative. So if I wait for it to come over here at the minimum, I should expect 0 in the derivative as well. Lo and behold, I get 0 electric field when I'm at a max or when I'm at a min. When do I get maximum electric field? Well, I would expect that when I have the greatest rate of change, and I know cosine has the greatest rate of change in the middle. So when this thing is in the middle, when it's at the cosine equals 0, then I've got the longest electric field vectors there, which tells me that yes, this thing is depending on the derivative. It's doing it in this weird right-hand rule way, right? It's not pointing in the same direction as the derivative. It's pointing perpendicular to the derivative. And now that I have that starting understanding of this, I can start to play around with it. For example, let's suppose I wanted to add a y component to the magnetic field. Let's suppose I just repeat cosine of time here, right? So I have cosine of time in the x, cosine of time in the y. What that means is that the let's look at the magnetic field first. What it means is that the x component is always equal to the y component, right? So it's always going to point at a 45-degree angle either this way into quadrant 1 or down this way into quadrant 2. And what you notice is that now my electric field vectors are doing something really interesting. Remember, they have to point perpendicular not to B, but to the rate of change of B, which happens to be in the same direction as B. Now, so they're still pointing perpendicular there, but they have this interesting little twisted ring scenario here. You might notice up here they do get to pointing, what is that? It's going to be along the z-axis, I think. No, what axis is that going to be? All right, let's restart. I want to figure out what axis that is. Okay, so for example, these are pointing, I had some of them going straight. Where were they? There we go. So for example, these, at some point here, they're going to point along the, I suppose that's, yeah, that is the z-axis. Yeah, so some of them are going to point along the z-axis there, kind of like they were doing before, but otherwise they're going to point along a combination of x, y, and z, which is pretty interesting. It's there. I can still evaluate these in a circle, right? I can still evaluate them in a ring that I've set up here, but now they've got this interesting twisted property to them because they have to point perpendicular to the rate of change of the B field. Okay, that's really interesting. Now, what might happen if I change one of these cosines into a sine? Let's run that and see what happens. This one I find really interesting. Remember that when you have cosine and sine, it's like you're tracing out a radius vector from the center of a circle, right? Because cosine squared plus sine squared equals a constant. So the magnitude of my B field is now not changing. It's only the direction of the B field that is changing now. It's rotating about the z-axis. And what you notice is that my electric fields now also rotate. What's interesting to me here is that the electric field now, it doesn't point perpendicular to B anymore, because remember, this thing is going around in a circle, and for a circle, the rate of change is perpendicular to the vector here. So let's go through this. So B is perpendicular to dB dt, and E is perpendicular to dB dt, and that means that B and E here are, on this side, they're anti-parallel, on this side, they're parallel. So this really shows you that you can get a scenario where the electric field is not perpendicular to B. It's showing this perpendicular to dB dt, which is pretty cool. All right, what happens if I move this cosine, let's say, over to the z-axis? So now it's going to rotate about the x-axis, which is significant because now it's rotating along that circle itself. And you might notice I've got this sort of wave propagating around the ring here, because now they're getting longer whenever the B field points in their direction. They're getting shorter whenever the B field points perpendicular to their, to their location, not the direction, to the direction of their position, which is really cool, right? So I've got this kind of like, and it's actually a double wave because I have a peak here and I have a trough here, right? Because I have these pointing along this way, I have these pointing along the other way. So it's really showing you what this perpendicularity looks like. And of course I can make all three of them oscillate. Let's suppose I do cosine of time, but let's give this one a different period. Let's say this one is cosine of time over 2 in the x direction. And so you can really get kind of any pattern to these electric field vectors that you like. You can add in more of these observation points. Really fun demonstration to help you understand better this really kind of esoteric concept. Now it looks nice and concrete because I can actually see what those electric field vectors look like.